Okay, morning all, and welcome to my talk on error resilience, low power integrity disorder. This work was done with Professor Naresh Shambar in the circuits group. I start by introducing error resiliency and then present integrity decoders as a test case for error resiliency. So as you stream down the transistor sizes to decrease power and voltage, there's increased variation in the transistor length and gate threshold voltage. So these variations this increased variation manifest themselves as increased delay, so that if the designer will design for the worst case, he has to consume a lot of power. Also, there is supply voltage variation. These variations are due to random particle hits, are due to leakage and crosstalk, as well as coupling between the different lines. Also, when you are reducing the voltage, the amount of energy needed to flip a bit decreases. So cosmic rays and particle hits can cause more increased rate of soft errors in your cell. Also, in high-speed design, reduced design margins and fine and multi-gigahertz clock operation makes your design more sensitive to variations. So the traditional view of circuits as error-free can no longer hold. So what we try to use is to employ error resiliency at very low overhead. So what's error resiliency? For example, if you take a full adder and you plot the percentage of input combinations versus the delay of one bit, you see that only a small portion of the input excites the critical path. So usually if you design for the worst case, you consume power to satisfy this as much delay as this point. However, only a small input of combinations are operating at this region. So what we do is that we decrease the voltage and try to correct for these errors when there is when an input excites the current. In particular, we use the algorithmic noise tolerance. So in algorithmic noise tolerance, we have a main block. In this case, it would be a Viterbi decoder, and this block would give an error-free output plus some intermittent error. And this error is usually large. What we add is an estimator for the main output. The estimator can be designed to operate error-free at low overhead, very low overhead and low voltage. So your only error is estimation errors, and usually this error is small. So by comparing the two outputs, if it's an error, if there's a large difference, we take the estimated output, and if small error, then we take the main block output. So if you look at it from the power and reliability perspective, your main block here, the blue curve, it's at worst case design at very high voltage, it's consuming very high power, and your estimator is not operating. As you try to decrease your voltage, your main block power will decrease, but you're paying some power on estimation and correction. So there's some optimal point of operation that is energy optimal. So why we choose the decoder as test case is used in different communication standards such as fourth generation LTE and WiMAX, and magnetic recording standards. It's usually it's required to support high data rates with large number of states. And for example, in a wireless LAN receiver, it constitutes 35% of the total receiver power. Power reduction schemes usually are circuit level, architecture, or algorithmic level. And all these techniques try to avoid error and assume the circuit is error. So in our approach, we use error resilience. We try to we can apply this error resilience on top of this approach to further reduce power. The Viterbi algorithm is a maximum likelihood sequence estimation that given received bits y sub I, it tries to find the maximum, the most likelihood received sequence. Your received bits is a combination of a state register, finite state machine, and your input bits, and it's represented by a trellis. The trellis has sets of states which represent the state of the encoder here, and depending on the input bit, it can have different transitions. And at each state, you accumulate a path metric which represents the reliability you have on each path in this trellis. And each branch has a branch metric, which is the difference between the received bit between the received bit y and c. In terms of architecture, you would have a branch metric unit here, which finds the difference between the between the received bits and the expected bits, and you have a set of add, compare, select units. These add, compare, select units are the main computational blocks. You have an add, compare, select for each state, and as its name implies, it adds the branch metric to path metric and compares the two possibilities and choose the minimum one. And the decision of add, compare, select units are stored in a survivor memory unit. These survivor memory units are used to trace back the trellis. In our design, we target 128 state. The rate have the target decoder is at the rates of 590 megabit per second. And our main focus is the decreased power of add, compare, select unit, as it is the main computational block here, and consumes around 60% of total power, 50 to 60% of total power. If you take a Viterbi decoder and try to decrease its voltage, so if its error freezes your bit error rate. But as you decrease, for example, from 1.2 to 1.1 volt, you have a large increase in bit error rate. There's two sources of errors in Viterbi decoder. Either you have an error in the adder or an error in the comparator. Usually, adder error will cause high increase in bit error rate because you're changing your belief on the path method, making the Viterbi decoder to choose a different path. For example, here we plot the path matrix evolution with time. So if one of the path matrix has an error, path matrix value would go low, and this is like by comparing it to the rest of path matrix, it would be the most optimal path. So there's this shift in path matrix evolution. However, if you look at comparator errors, we can tolerate a small number of these errors because the path matrix is correct, but I'm choosing some a less likely path. So depending on the percentage of these errors, your increase in bit error rate is still tolerable. There's the red and the blue curve here. So first step we did is we relaxed the comparator design. I won't go into the details of the architecture, but what we did is that we divide our comparator into two sections, and one based on LSB and one based on MSB, and give more priority to MSB. And then, so this type of architecture would have only a limited amount of decision error, but most of the time our decisions are correct. Then we included an estimator for the add, compare, select output. This estimator depends on is a reduced precision estimator of the main clock. And then we have an AND decision block here, which compares the main block output to the estimator output and selects the correct one. In terms of bit error rate performance and power saving, you see that here is the original curve at 1.2 volt. Conventional architecture, if you decrease to 1.1 volt, it will operate at that curve here. However, in our error resilient design, our bit error rate is still tolerable. You see this variation. For example, this when we move from 1.2 to 1.2 volt to 0.9 volt. However, if we decrease lower than 0.9, for example 0.8, our performance would be at this point here. This is because our estimator also starts to fail. In terms of variation, process variations, you see this is the variations caused in convention, but in our architecture it can behave at this point. So this is the variation. Here we see the bit array distribution of conventional architecture. It's very high, 0.4 to 0.5. However, in our design at 2 dB, we take 2 dB, it's still, these are the variations shown here. In terms of power saving, we can have 25% power saving at the slow corner, process corner, and 40% power saving at the nominal corner, process corner. Another technique we introduced is state clustering. So you have, so in the trellis, you have an add compare select for each state, and these states can have close path mapping. They share the initial set of states. So we can design one state as an estimator and use the other and allow the other to induce errors, and use this estimation state to correct for these errors. This estimator can be within one of the states of the trellis, or it can be some additional fictitious state we add, so that it's like its path matrix lies equidistant from all nearby states. In terms of performance of this state clustering, we see here we can decrease our voltage from 1.1 up to 1.2 up to 0.9 volts. This is the bit array performance. However, conventional is still very high. And in terms of variation, process variation, our design is very robust to variations. It's just 0.5 dB, and the conventional architecture shows high bit array dB. And in power savings, we consider nominal corner. We have around 71% power saving here, as compared to conventional architecture. And at the slow process corners, due to process variations, we have around 44 to 62% power savings. Also, we can do error analysis on this type of approaches, and we've derived error bounds we have derived we derived how the error bounds will vary as we decrease your voltage. So we can bound the probability of error by some code parameters and some probabilities of error that depends on your voltage reduction. And this loss in coding gain is also verified by simulation. So in conclusion, we have presented error resilient architectures for add compare select and viterbi decoder. And usually in this decoder we always have trade-off between reliability and power. So we need more robust design at very low overhead power. And algorithmic noise tolerance emerges as a promising approach by bridging system level to circuit level techniques. In extension of this work, we're working on spatial and temporal distributed estimation. So instead, so in your trellis, so in the trellis shown here, different states may exchange their estimates on the output. So your estimation will be more distributed, and we expect to have better performance. Thanks all. Hope you have any questions.
I have a question. So you add, in order to counter error, you add an estimator block or something, right?
Mm-hmm.
So that also would consume power.
Mm-hmm.
So
usually this is the power of this estimator. So the estimator here is around 20% of the main block. However, its power is still small as we reduce voltage here. But at very low voltage, if we need to ensure correct operation, we have to do very high.
okay, so if voltage goes,
very,
the
very
trade-off
low.
would start
Yeah.
coming in.
Mm-hmm.
Okay.
Then that is.
All right. Thanks a lot.
Okay, thanks.